To show you what we can achieve by these compositions, let's consider the following combination of gates. Now with a few more of these Hadamard gates, acting again on 2 qubits. But there are now 2 Hadamard gates acting on both qubits. And if we would leave it at this, we would simply obtain the square of the Hadamard gate acting on each of these qubits. But this is simply the identity matrix, so this would be really boring. But all of this changes when I again use the controlled NOT gate and now place it exactly into the middle of these operations. One can again determine what this combination of gates is doing to a quantum state in different ways, but one very straightforward way is to just multiply the corresponding matrices. Well, we have 2 Hadamard gates acting on each qubit at the beginning. This accounts for these 2 Hadamard gates here. And the order of multiplication of these matrices actually does not matter. They act on different qubits, so they are really independent of each other. And mathematically, these matrices simply commute. Then we have the controlled NOT gate. And then we have again another Hadamard gate acting on each of these 2 qubits. So these are these 2 here. So this circuit is of course mirror symmetric, but I thought I better point out again what the proper order of these matrix multiplications would be. Now each of these Hadamard matrices here and here we have seen before, and this one we have seen also before, so we can simply insert these expressions. And these are now matrix multiplications of several 4×4 matrices, so you can definitely work this out, even though it might take a little bit of time. But I'm just going to give you the result, and this result looks as follows. So this will be a 4×4 matrix with the following entries. And in order to interpret this, we are now going to convert this into a truth table. So I'm going to write down the different basis states, which correspond to different basis vectors. And I can multiply these vectors and obtain certain results that I can convert back into quantum states. And in particular, we see that the first state will not be changed. But this state here will become the last state. Essentially, this is now a permutation matrix between the second and the fourth entry in the vector. So this is actually interchanging the second and the fourth basis state. So the result looks like this. So this is our truth table corresponding to this matrix. And now we can have a look what this means operationally. And then we see that there are 2 states that have not changed. And what is characteristic about this is that in these, the second qubit was 0. And 2 states have changed. Namely, the first qubit has changed its state from 0 to 1 or from 1 to 0. Now this again happens exactly when the second qubit is 1. So this has a very straightforward interpretation, namely as a controlled NOT gate, but one where the role of the first and the second qubit has been interchanged. So it's now the second qubit, which is the control qubit, and the first qubit, which is the target qubit. So following our earlier convention, to indicate these 2 different rows of the qubits, we call this C21. So this is a nice result. We can see that we can replace this complicated circuit by a simpler one. And we obtained it in a very straightforward way, namely by just multiplying matrices. So we could certainly stop here. But when we then step back and have a look at our original circuit, then we are going to notice something very curious. Because when we think about this controlled NOT gate in classical terms, then it seems to indicate that there is a part of the world which is affecting another one, in the sense that we have a very well-defined cause and effect. So we have sort of a cause, and this gives an effect on a different part of a physical system. But in this classical interpretation, and the C0 gate is essentially a classical gate, there is no effect in the opposite direction. And around this we place operations which simply modify the two different parts independently. But what we ended up is with a gate that effectively has one part of the system affecting the other one, but in exactly the opposite direction. Now this sounds a bit like a miracle or maybe a magic trick, and certainly it would be like magic if we would do this with a classical system. So this would not be possible for a classical system, because in a classical system on top of this we would be doing this with definite states of information. But here we have a quantum system in which we have superpositions and in particular also entanglement. And once we have entanglement, then there is no clear division between the different parts of the system anymore. Well, when one looks behind the magic screen in this case, then we recognize that we here have a very important component, namely our entanglement circuit. And so this circuit definitely involves a bit more than just classical effects, in particular superpositions and entanglement. And therefore dividing the system into two different parts no longer makes sense, and we can achieve effects of this type. Nonetheless, this is really just the inner working, so effectively we start with states of well-defined information and end up with states of well-defined information, and we use the magic only really in the middle. And when we later look at algorithms, in particular for quantum computation, then this is a very common feature. So the goal of these algorithms is to do something very specific and very predictable, to start out from very well-defined states of information and to end up in such states, but use quantum resources in the middle.